In this lesson, we'll continue our discussion on learning target number 2, focusing on Charles's law, which describes the relationship between the volume and the temperature of a gas. A scientist named Jack Charles discovered a direct relationship between temperature and volume. If the temperature of a gas goes up, the volume of the gas goes up, and vice versa. This occurs because at lower temperatures, gas molecules slow down and press on the walls of the container less. If you have an expandable container, as temperature decreases, the volume decreases. This is shown in the graph. As temperature decreases, so does the volume, so it's a direct relationship. Now, if you extrapolate this graph backwards until you get a theoretical point where it hits the x-axis, the volume of the gas would be 0. Lord Kelvin noticed that no matter what gas you use, the theoretical point where you hit the x-axis was always the same, temperature, minus 273 Celsius. Lord Kelvin named this absolute zero because this is also the theoretical point that all particle movement stops. The particles simply have no energy to do any vibrational motion at all. This is therefore the lowest temperature a substance can ever reach. Scientists have looked for substances that are at absolute zero, but they still haven't been able to find any. Even in the darkest reaches of space, objects have about a 0.4 Kelvin temperature. Some scientists think that this little bit of heat that this matter has is left over from a big explosion at the beginning of the formation of the universe. Lord Kelvin devised a new temperature scale based on absolute zero, called the Kelvin scale. This is also the SI unit that scientists report temperatures in. Because it starts at 0 and doesn't have any negative values, it can be incorporated into math equations, unlike Celsius and Fahrenheit. It's pretty easy to convert into kelvins. All you do is you take your Celsius temperature and add 273. It's important to note that on the Celsius scale, it's degrees Celsius as the unit, but it's not that way for Kelvin. It's just simply K. There's no degrees. Try out example 1, converting these Celsius temperature into Kelvin. Pause the video until you have your answers. Here are the answers for example 1. Remember your SIGDIG rules for addition and subtractions. Your answers should have the same number of decimal places as the lowest number in the question. So, for example B, I have 25 degrees Celsius. That's got no decimal place. Neither does 273, so I can't have a decimal place in my answer. Now some people will get weirded out and think, oh, I have 2 SIGDIGs, I need to round this to 2 SIGDIGs. But that's following the multiplication and the division rules. Remember, when we're adding, we count decimal places. The same thing happens for question C. I may have 2 SIGDIGs, but I need to count decimal places when I convert into kelvins. Let's look at the formal definition of Charles's law. It states that the volume of a fixed mass of gas is proportional to its Kelvin temperature when pressure is kept constant. It's really important to note that this relationship only is true if you're comparing kelvins and volume. Mathematically, we can represent this using the proportionality statement V varies with T. Because it's a direct relationship, volume and temperature will be in the same place, both in the numerator of this equation. If I want to change this into a math equation with an equal sign, I have to introduce a constant to fix the relationship so it's exactly perfect for any real gas. Because this is the second gas law, Charles' law constant is known as K2. Now we don't want to have to look up the K2 constant for the particular gas in every question that we do. That would be a lot of time spent looking on the tables or on the internet. So let's get rid of this K2 constant by taking a balloon and having some sort of initial conditions. So let's say, for example, we have a balloon taped to a lab bench. I know its initial volume and its initial temperature. I'll represent that by doing V1 and T1. Now K2 is the constant for the gas that is in that balloon. Let's say it's pure oxygen gas. If I then pour liquid nitrogen onto this balloon, the temperature will change, and so will the volume because of the result. I'll label that V2 and T2. Now, as long as I don't open the balloon and change the gas that's inside of it, if I still have oxygen, in this example, K2 is still going to be in the equation, and it's still going to be the same value. If I rearrange both the initial and the final equations so that they say K2 equals, I get V1 over T1, and on my final side, I get V2 over T2. And because K2 is the same value, simply because I'm using the same gas, I can make these two equations equal to each other. And this is the form of Charles's law that we're going to use. V1 over T1 equals V2 over T2. Now, just like Boyle's law, Charles's law equation has some conditions on it. We've already mentioned the first one. The temperature must be in kelvins in order to use this equation properly. The second is that the pressure on the gas needs to be constant. If the temperature and the pressure change simultaneously, we can't use Charles's law. Thirdly, the amount of gas needs to be constant. I can't open the container and change the amount that I have. And finally, Charles's law only works when you have a gas that's in a flexible container, like a balloon, or a syringe, or a piston. Let's try out some Charles' law calculations. In example 1, we have a 1.2 liter balloon that's inflated with 37 degrees Celsius air. Then it gets dipped into liquid nitrogen, which is at minus 195.8 degrees Celsius, and we're asked to find what's the final volume of the balloon. Because I have two temperatures and one volume given to me, and I'm asked for a second volume, I need to use Charles's law. It's the only one with two volumes and two temperatures in it. Let's sub in what I know. The initial volume is 1.2 liters, and 37 degrees Celsius converted into Kelvin works out to be 310. I want to know what the final volume of the balloon is at minus 195.8 degrees Celsius. That's 77.2 Kelvin. If I rearrange for V2, this gives me 0.30 liters. Now when I'm talking about sigdigs, I am only allowed to have 2 in my answer. That's because my initial volume is 1.2 liters, not because I have 37 degrees Celsius air. As soon as I take 37 and add 273 to get 310 Kelvin, that becomes 3 sigdigs. I need to take my temperatures in Kelvin when I count my sigdigs to come up with my final answer. Here I have 3, here I have 3, here I have 2. I need 2 sigdigs in my answer. Try out example number 2. It uses Charles' law, but you have to rearrange for a different variable. You should be able to plug in what you're given and rearrange for what you need to find. Pause the video here until you have your answer. Here's the answer for example 2. Let's sub in what we know. We have a bag of air that is 36.0 mils, and it's at 5.0 degrees Celsius. That's 278 Kelvin. After the bag has been left out, it has a volume of 39.4 mils, and we're asked to find the final temperature. Now there are a couple of different ways that you can rearrange for T2. Some people like to simplify what this fraction is in one step and then do the Berg switch so that T2 gets by itself. What you don't want to do is divide these two and then divide by 39.4. That will give you 1 over T2, not T2. The most common method that people use is cross-multiplying. I take these two and multiply, but that will equal those two multiplied together. So 36.0 times T2 equals 278 times 39.4. Then all I need to do is divide both sides by 36 to get T2 by itself. This gives me 304.25 Kelvin. Now, because you're unfamiliar with Kelvin, you've just learned it, that number might not make a whole lot of sense. So if we subtract 273 from it, then we'll get our final temperature in Celsius. And then I need to round for sigdigs. Because I have 3 sigdigs in each of my numbers that I've subbed in, I can keep 3 sigdigs in my answer. Complete the Charles Law questions listed on your Unit 5 assignment cover sheet.